Hey everyone, in this video we're going to be working on a skill called linearization, which is really simple. It's just doing something we've already done a million times, making a tangent line, and then just using it to approximate some function value nearby where we made the tangent line. So I've got a function here. It's a simple quadratic. Why isn't my page scrolling? That's really nice. There we go. Now it's working. Okay, so I got a function printed here. It's a quadratic. And the first thing we're going to do is find the tangent line at x equals 2. So what two things you need to make a tangent line? We need a point, and we need a slope. So x is 2. Hey, we don't even have to do the math if we don't want to, because it's right there. But I guess we will need to take our time to figure out the derivative. So f prime of x would be 2x, which then if we just evaluate that at x equals 2, we get our slope at that point would have to be 4. So, like in the past, if you just said, hey, make a tangent line, you'd just write, okay, my tangent line is y equals 4, and you give it in point slope form, x minus 2 plus 5. Sometimes the notation in textbooks or on the AP test for that matter will say, hey, your linearized model, and they'll want you to give it a different name, and typically that name is L of x, where the L just stands for linearization or linear approximation, whatever. But it's quite literally no different at all. And then draw our tangent line on the graph. Zoop. So let's see. Well, we had a slope of what? 4. So there's my tangent line. Cool. That is zoomed too far out. This will do. Okay. Up next, like I said, we're going to use the tangent lines for something. Use your linearization to approximate f of 2.1. Compare this value to the actual value of f2.1. So how about, let's say, f of 2.1? Well, that would be approximately the value that our linearization, or our linearized function, is going to give us when we plug in 2.1, which, when we do that, that's easy. We have an equation for that. Not that the first one wouldn't have been easy as well. So 2.1 minus 2 plus 5, which, doing the subtraction there, gives us 0.1 left over. So I think we get about 5.4 for our approximation. And then if you plug 2.1 in to the original function, well, you got to square it, which is kind of annoying to square a number with a decimal. Because it's 2.1, it wouldn't be that bad. But I know you know how to work the buttons on a calculator. I'll just tell you it comes out as 5.41. So our estimate was pretty good. It was a little low, but whatever. Most importantly, our estimate was just a tiny bit low, which is a question AP loves to give with this stuff. They say, is your estimation an under or over approximation? So, here's my part C. Your estimate in the previous item is an underestimate. Why? So, take a second and think about that. Maybe pause the video. Why is using this tangent line going to give us an under approximation? Did you think of anything? Okay, well, it has to do with the curvature of the graph. This is really important. F of x is concave up. Look at, I mean, it's a quadratic, right? It's concave up. That means that the slope is always increasing. The slope is always increasing. That means, like, if we use a constant number for the slope, or how about this? So, because we used a static or constant, I should have just used the word constant. for slope, we were guaranteed to have an underestimate. And again, that's just because the slope on the OG function is always increasing, and we built something whose slope isn't changing. So the original function is getting bigger at a faster and faster rate, while the linear function is getting bigger at a constant rate. So it's always going to give us um, an underestimate, assuming we're working in the positive side of things, like above the x-axis, which we almost always are for this style of problem. If you want to generalize this beyond this specific example, what you could say is if the function f is concave up, then your linearization will always be an underestimate. And then you've got the converse, or the opposite of that statement. If the function is concave down, then your linearization is always going to be an overestimate. Some people treat these like two facts they have to memorize. You can also think about, as long as you know your 12 basic functions, you can visualize what an equation would look like without actually punching into your graphing calculator, you can usually figure it out. Whatever works for you. All right, let's turn the page. So example 2 is just more the same. This time I didn't give you a picture, gave you a slightly more annoying function. So this time our OG function is natural log of 2x plus 5. Our job is to figure out the linearization of that model. We're going to center the linearization at x equals -2. That just means that's the point we're using to build the tangent line. So let's see, how about our point? Am I recording? Okay, good, I am recording. For a second there, I thought I was talking to myself like an idiot. I'm always talking to myself. Okay, so we plug in 2, get the natural, sorry, -2, we get the natural log of -4 plus 5, so natural log of 1. Natural log of 1 is 0. And then we need our derivative to come up with the slope, so f prime of x. Let's see, it's the natural log rule, so 1 over the inside, and then don't forget the chain rule, times 2. Or you can just put the 2 up top if you noticed it right away. So then our slope is going to be f prime of -2, which would be 2 over, let's see, 1. So 2. Okay, so then our tangent line, or our linearization, because we're going to make it sound fancy this video, would be slope x minus x value, and then plus y value, so plus 0. Here's what we got. 2 times x plus 2. Okay, then our job is to use this approximation to approximate f of -1.9. So f of -1.9 is approximately our linearization at that same value, which, I mean, here's where the linearization comes into play. Like, it is easier to evaluate this without a calculator. It is easier to evaluate something linear without a calculator than something else like natural logarithm. Of course, I'm sure you're screaming at your phone or your laptop, Mr. Doolin, we have calculators. I'm aware. What can I say? It's in the curriculum. So anyway, let's punch that in. So slope -1.9 plus 2, which would be 2 times 0.1, which would be 0.2. Is our estimate an overestimate or underestimate? So you could say, well, Mr. Doolin, I'm pretty sure the natural logarithm function is always concave down, but you could just check it too, you know? You could say, okay, well, what's the second derivative here? because then that if the function is concave up or down at that single point, that's what's going to tell us if our approximation is an over or an under estimate. So where's our first derivative? There it is. Okay, just because I don't like quotient ruling, sometimes it gets really messy, I'm going to rewrite the first derivative as 2 times 2x plus 5 to the negative 1 power, just because then it's easier to derive. If you want to chain and then evaluate it later. If you want to quotient rule it, be my guest. Okay, so constant multiple, the 2 just comes along for the ride. And then we'll bring the exponent down, keep the inside the same, subtract 1 from the exponent, and then don't forget the chain rule. Derivative of the inside would be 2. So squeeze this all together, turn it back into a fraction. 2 times 2 is 4. We'll make it negative because of the negative 1. And then we got the 2x plus 5 squared. We'll send that to the denominator. Okay, so if I was to plug in negative 1.9, so let's just say f double prime of negative 1.9. We're not actually going to evaluate it, so maybe well, we could use an equal sign here. How about negative 4 over... Here's what I'm going to do. We've done this a few times, especially when we made sign charts. I'm just going to look, is it positive or negative? Because that's all I care about. Is it concave up or concave down? Well, I got a negative number up top, and then 2 times negative 1.9. Well, that's going to be a little bit less than negative 4. Plus 5, okay, now it's positive. Squared, still going to be positive. Negative number divided by a positive number is going to give me something negative. So that would make f concave down, which then makes our linearization an overestimate because the function is curving away. So this is going to be the easiest version of concave down. If we had a tangent line like this, our function is curving away. It's curving underneath our tangent line. So that's why it's got to be an underestimate. Our estimate is an... Sorry, did I say underestimate? Ugh, it's an overestimate. And here's your justification. The problem didn't say justify, but you know me. I like to make you justify things. Your justification is because f is concave down. Okay, so here's a more, I want to say practical application, but I know you'll call me on it. So here's an application where it's not as straightforward. We're going to approximate a number that we probably have a pretty hard time figuring out by hand using linearization. So the number we're tasked with approximating is the 4th root of 82. Well, okay, how are we going to get there? Let's start with the 4th root function. So let's just say f of x is our is the 4th root. Words are hard. You get what I'm trying to say. Okay, so you know what's really nice about 82? It's really close to 81. And I know the 4th root of 81. Hopefully you do too. It's 3. Aha. So what if we built our tangent line or our linearized function over here where it's really easy to evaluate, and then we approximate the value at 82. So let's see, what do we need? Point, slope, right? So let's get on that derivative. Okay, so, well, the slope's kind of going to be a little messy to come up with, but, whatever. We can do it. So how about 1 over 4, and then, let's see, this would be 81 to the, whoops, it's 3/4, not 4/3, my bad. 81 to the 3/4, and that'll give us some number. And then, of course, for our point, which I forgot to notate earlier, so f of, well, I marked it over here, but f of 81. That's going to give us 3, so our point is 81, comma 3. Back to evaluating the derivative. Now, if it's been a while since you did the fractional exponents on something, 81 to the 3/4 is the same thing as the 4th root of 81. And then you can choose. You can either cube it before doing the 4th root, or you can cube it afterwards. In this case, I'd recommend cubing it afterwards because I don't know what 81 cubed is, and I don't want to take the time to figure it out. We do know the 4th root of 81 is 3, and then 3 cubed is 27. So our slope is going to be 1 over 4 times 27. Well, still not great, but there we go. So our linearization, it's our tangent line, so slope, point. Now we're ready to go. We want to approximate f at 82. Well, that's going to be about L of 82, which is 1 over 108, 82 minus 81. So that's going to be 3 plus what you got left over here, 1 over 108. And shall we leave it at that? Let's compare it to what it actually is. Okay, so this number we came up with is about 3.00926. And then the actual 4th root of 82 is about 3.00922 is what we'll call the last digit. So, pretty close. Okay, I'm running long here, but I suspect you don't need me to narrate how to work through another problem when you got 2 or 3 to compare to. So on the back page, there's one more. I'll have you try it before class tomorrow. The only thing I want to remind you of, it's probably been a little while since we've used the word secant line, or just like secant in class. Remember, a secant line is a line that cuts through 2 points on a function. So in like part D here where it says find the equation of the secant line between these 2 points, that would be you've got your function, what's a square root, so it's going to look something like this. And the secant line would be the one that passes through, say, 2 points. So go ahead, pause the video, give it a try. You got your linear approximation, over-under estimate, compare it to secant line. And then in a couple seconds here, you'll see the answer pop up on screen. Okay, so here you go. There's our linearization, the approximation. I would pause the video so you can compare here real quick. You may have had to, remind yourself, whoa, secant line, how do I make that? Just get yourself the slope from a couple points, then go point slope form. The only thing I hope the only thing you had to stop and think about a lot was f is going to be an over and under estimate, which I think the easiest argument here is just to make a visual one. The function's concave down, always for your estimates, justify whether they're over or under estimates using concavity. Since the function is concave down, look at how the secant line cut through it and stayed below in between that interval. So there you have it. Thanks for watching, and I'll see you tomorrow.